Welcome to another segment of High School Geometry with Netz and Weichel. This is Mrs. Netz.
And this is Mrs. Weichel.
And today we are looking at 6.2 Triangle Similarity. So, what are we going to be learning about? Well, by the end of the lesson, you will be able to determine if triangles are similar through the use of similarity criterions. Very much so like our congruent
criteria.
Yep, absolutely. So, learning something that we've already learned before with just a couple.
Taking a different spin on it.
Yep, absolutely. So why do we need to know this? Well, knowing how to determine if two figures are similar or congruent by investigating similar and congruent figures is really important. Like, are they kind of the same? Are they exactly the same? That's maybe something good to know. So how will you know it? Well, you can identify or verify congruent and similar figures and apply equality or proportionality of their corresponding parts.
All right, so in our last lesson, we learned about dilations, and actually dilations create similar figures. So when you're resizing a shape, you have to do it in a way that it is making the shapes proportional. So I use the letter J. What you can see here is that figure 1J is similar to figure figure 2J. I rotated, maybe reflected a little bit, translated, definitely dilated though. So dilations are a big part of today's lesson because our shapes are not congruent, they are similar today. Going back to this, just with the letter J, you can't just stretch it one way. So similar again to what we did in our previous lesson, 6.1, you have to take that lower right corner and drag it out so it's expanding both horizontally and vertically.
You don't want a tall, skinny J. It'd be weird.
So similar is when you have two figures that are similar, if and only if one figure maps onto the other through a single or sequence of similarity transformations. So in Unit 2, we had our rigid transformation unit, and all of those were producing congruent figures. Now we're looking at similarity transformations where we're introducing the whole idea of we can resize it. So similarity transformations are a series of any number of finite dilations and or rigid transformations. So again, I feel like I've said this 3 times now, I'm going to say it again. Any of the rigid transformations could be used. So reflect, translate, rotate. But we also have finite dilations, meaning it doesn't it's not constantly changing. Finite just means it's countable, has a start and an end. So you could do a single dilation or 2 dilations or 3 dilations. Those are all finite.
Finite, think of finite meaning finish.
Exactly. The similar symbol you can see right here. It's just the top part of the congruency sign. We've taken the equals part off of the congruent sign. So similar is just the little squiggly line. Similar figures, they're going to have corresponding angles remain the same. We talked about this a little bit when we were doing dilations. Dilations, the angles didn't change, if you remember from our previous lesson. So similar figures, the corresponding angles do not change. So off to the right side, you could actually draw these 2 triangles, and then I would go ahead and mark the angles that we know are congruent. Obviously, angle L and L prime are congruent because I have those right angle marks. H and H prime would be congruent, and S and S prime would be congruent. So whatever H and S are, H prime and S prime would be the same thing. Now we're going to talk about corresponding sides. The sides are not going to be the same. The sides are definitely changing. Our shape got smaller, so this is a shrinking dilation. So when you look at this, I threw in some numbers. These numbers do not have any significance. It's not the actual lengths. I didn't measure them. I just threw in an example. If HL is 6 and H prime, L prime is 3, we could write a fraction showing an image over the pre-image would be 3 over 6. So you can see that H prime, L prime became half as big because 3 over 6 is 1/2. The other numbers I chose follow the same pattern, and that's the thing that you guys have to watch for, is that are all the sides shrinking the same exact rate, or are they all enlarging by the same exact rate? So here you can see we started with a hypotenuse of 10 and it shrank down to 5. So 5 over 10 is also 1/2. And then we started on the base down here, LS is 8, and it shrank to 4, which would also give me a 1/2 ratio. So because all of my sides shrank by a half, I can say that these are similar figures because the corresponding sides are proportional. Proportion means that you have multiple ratios that are equaling the same thing.
You can almost think of it like as if you have like 12 cupcakes. If you take every single one of those cupcakes and cut them in half, you cut them all the same. Everything's the same. So now you have half the cupcakes. So you have to cut like every single part of every single cupcake the same. So you basically, or like take a room, and I want the room to be half as big. Well, you would cut the whole, both sides of the room in half.
So the next part, you're going to need a compass and straight edge. You guys had a question like this on one of your previous tests where you were proving congruency through rigid transformations. Well, now we're going to show how similar transformations or similarity transformations can map one shape onto another. So please have your compass and straight edge out for the next 3 problems. So I personally always start with a translation. And your test was the same way. I want, because I'm trying to get one of my shapes to map onto another one, let's go ahead and line 2 of the vertices up together. Well, I know that D and A are the same. How do I know that? Look at the name. A is first, D is first. So when I'm mapping one onto another, I need D to map onto A. So the first transformation that I did was I translated triangle DEF, and I'm working with that one because it's smaller. It's going to be easier to move because it's a smaller area. I'm going to translate it over. And I'm having you use a compass and straight edge loosely here. When I say translate it, we're going to take D over here. E should be translating in a congruent parallel manner, and so should F in a congruent parallel manner. So you should get this figure. The next thing we're going to do is we're going to copy angle D at angle A. So here's where your compass can come in. So we want angle A and D to be copied. So you all should remember how to do this. It was just 2 chapters ago. You're going to draw
most of them did a huge project.
And you just turned in a huge project for this. So you draw your arc on both angles, and then you measure right here, and then you copy that measurement. And by doing that, what should happen is, and you can measure D to E, make sure your triangle is the same, you're going to end up with D double prime, E double prime, F double prime by rotating that around a little bit by copying that angle. The next thing that you're going to do is we're going to copy angle E at angle B. And how do I know E and B are mapping to each other? Well, again, I can just look at the letters. I have B second and E second. So you can see right here I have E double prime. I drew my arc, and then I'm going to do the same thing at B. And what should happen is you should see that E double prime is congruent to B. And by doing that, seeing where they meet up, I'm hoping you can see that D double prime, or triple prime now, E triple prime, F triple prime are all mapping right on top of A, B, and C. So all I did was I took triangle DEF and translated it over here at A. I copied angle D and I copied angle E so that they're right on top of A, right on top of B. And the resulting figure is that the triangles are congruent. And if you think about what we used, we copied this angle, we basically copied this side by moving E down to B and copied this angle. That would be your angle side angle. Right here would be your angle side angle based on the material we used. We didn't do anything over here on the right side of this triangle. Because I was able to translate, technically rotate, and then technically dilate, because I used those series of similarity transformations, not only do I now know that these 2 triangles are congruent, you can say the original 2 are similar by something called angle-angle similarity. That's your first similarity criteria. and we're going to do the similar things on the next two problems. We are going to take triangle RED and we're going to map it onto triangle BIG. So I'm going to start the same way. I'm going to take point R and map it to point B because those are the first two letters in our triangle names. And if I translate it along this vector, well, D is going to translate in a parallel congruent manner, and so is E. I need the other 2 points to map on to I and G, so the first thing I'm seeing, if I'm thinking in the world of rigid transformations or similarity transformations, this triangle needs to rotate around. So I'm going to copy angle R at B so that that technically gets rotated around. And I'm saying copy the angle so that as you're doing these, they map onto them. Again, technically that is a rotation, but unless you want to get your protractors out and measure them, I think copying the angle is going to have the same result. All right, the next thing we're going to do is we're going to do a dilation. We are going to double the length of RE. So if you measure R to E and go a second time like we did in 6.1, hopefully you're seeing that E triple prime here is actually mapping right on to I. And when you double the length of RD, D triple prime is actually going right on to G. So we were able to create two congruent triangles. And based on the criteria that I gave you, we actually proved it through side angle side because we doubled this length. So now I know that BI is the same as R triple prime, E triple prime. And then over here, I know that BG is the exact same length as R triple prime, D triple prime. Because I was able to use rotations, translations, and dilations, you can actually say that the two original triangles are similar by the criteria of side angle side similarity.
Not too bad.
Not too bad. All right, and then the last one, there are three similarity criterions. We are going to just take triangle MAN and map it onto triangle SOX.
Let me guess. We're going to translate point M over to point S.
We are, because they are the first two letters, and translations I think get at least one of the points where it's supposed to be, so now it's not going to move. What I'm noticing is we have kind of the same triangle. They're definitely different sizes, but this one's going the opposite direction. So I'm going to, again, loosely, I'm not asking you to construct this formally.
We can just flip it over,
We're going
right?
to flip it over. Again, I'm not going to have you draw perpendicular bisectors and do it all fancy. We're just going to kind of sketch it so that it maps onto those other two sides. Definitely, hopefully you're seeing we're on the right track here. We're going to measure M double prime, N double prime, and we're actually going to triple it. So by measuring it and just dilating that N double prime away from M double prime, you end up going 3 times, and the result after going 3 times is that your last points are mapping on to where it's supposed to be. Same going down vertically here. Here MA, if you triple it, MA ends up mapping onto SO. So the result is you have two congruent triangles. They're congruent by, I didn't talk about angles at all. All we did was triple all of our side lengths. So by side, 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 we can say that these triangles are congruent. Because I was able to create congruent triangles, you can say the original two triangles are similar by side, side, side similarity.
Very cool. How about we, I don't know, sum all this up?
So let's make this a little bit more clear. You guys have a table at the bottom of your paper where you have 3 triangle similarity boxes. We're going to just basically take the 3 we just constructed and put them nice and clean down here. So the first one, you can go ahead and write this above the words triangle similarity, would be your side, side, side criteria.
Or SSS in the similar sign?
Yes, and I would maybe write that along the bottom. You guys have a little bit of a space down at the bottom. This can be abbreviated to SSS, similarity symbol. You want to make sure you include that similarity symbol to differentiate between congruence versus similarity. So just side, side, side would be congruence. All right, and then to be side, 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 what that means is your sides have to be proportional to each other. So I'm going to go ahead, I just use random numbers. Again, they don't have any significance. Let's say the OH is 2 and AC is 6. Well, looking at those, I could say that this is a 1 to 3 ratio because 2 over 6 is 1 over 3. Then let's look at HP. If I say HP is 5 and AE is 15, well, 5 over 15 would also reduce to 1 over 3. And then lastly, if I look at PO and compare it to EC, I get 4 over 12, which reduces to 1 over 3. So because all three pairs of sides create that 1 over 3 ratio, the triangles must be similar by side-side-side similarity. Next is going to be side angle side similarity. So you can go ahead and write side angle side, and then maybe underneath write SAS with a similarity sign underneath it. For this, it's going to look very similar to what you guys learned in Unit 3. To do this, you would need to know that you have a pair of congruent angles. So angle C and angle O I picked. So you can go ahead and mark angle C and angle O congruent. And then for the S's, you know the S's are going to include the angles I've chosen. But we're not looking for congruent sides now, we're looking for proportional sides. So you need numbers. So I just went ahead and made some numbers up again. 10 over 5 would be a 2 to 1 ratio. And then so would 24 to 12. So because I'm creating that 2 to 1 ratio, we know that that would be a proportional relationship. So there is your side angle side similarity, what it's going to look like. Just a mental note, if you are going to say side, 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 or side angle side, you have to have numbers to see if they are proportional, or congruency signs to make, you can put in numbers to see if they are proportional. But 99% of the time, we will give you numbers if you have to use them. And then the last one is angle similarity. So if you have two pairs of congruent angles, you know the triangles are similar. So if you remember, we told you never use angle, angle, angle. Well, that was for congruency. If you know that you have angle, angle congruency, then you know the triangles are similar. And I'm going to go back to the equilateral triangle. All equilateral triangles are similar to each other. They're proportional to each other, yet all three angles are always 60 degrees, no matter how big or small it is. So if you just have congruent angles, you know that the shapes themselves are similar. So I went ahead and added in my congruency marks so that you can see that you would be able to say that we have similar triangles.
For some of you, it may be easier to think or process a square. No matter how big or how small a square is, it doesn't matter. The angles will always be 90 degrees each. I could draw a square that was 100 feet by 100 feet. It doesn't matter. The angles are still 90 degrees because we know our properties of parallelograms.
Yes, we do. Hopefully we do. All right. The next page is just actually creating some equations to work out using these proportional relationships. So with this one, in order to be able to answer it, we're going to reach back into chapter 3. We're giving you parallel lines here. Parallel lines that are connected by a transversal.
Oh, you better mark your vertical angles right now or I will lose my mind.
So we have our vertical angles here. And I'm going to lose my mind if you do not mark your alternate interior angles. So you actually have all three pairs of angles congruent through vertical angles and alternate interior angles.
Wait a minute. Don't we just need two angles to say they're similar?
We do only need two.
So
in this one, we know all three though, so it doesn't really matter which ones you look at. I'm just highlighting so you guys can quickly see the alternate interior angles. You can see them there, and you can see them also right here.
Now, one of the things that I have found is students will oftentimes compare the side with the X with the side with the 4. Here is a trick that will help you to make sure that you start comparing same parts to same parts or corresponding sides to corresponding sides. Now that we have all of our angles marked, let's use them to help us out. So, for example, if I needed to name these two triangles, I would go ahead and name the first one right away, and I'm going to go ahead and call the very first one ABC. Now, I know to go from A to B, I've got to go from an angle that's marked with 3 marks to an angle that's marked with 1 mark. So I need to go to my other triangle and do the same thing. Where do I go to get from 3 marks to 2 marks? Well, angle D has 3 marks and angle E has 2. So I go from D to E and then to C. It's so important that you make sure you are looking at same parts and same parts. Please use those congruency markers to help you get them matched correctly.
So you can see here that where we have EC, we also have BC. So that means that EC and BC are actually the corresponding sides. So we would put them together as a ratio.
So you know EC and AC are not compared.
You also, by looking at this, can see that the other side we have, BC. Okay, I said that wrong. I apologize. I was looking here. BC is 8. No, I didn't. Never mind. I'm confusing myself. All right, so sorry about that, everybody. 4, looking at the 4, we have A and C, which are our outer 2 letters. That would be compared to DC, which is 6. So X is compared to 8, and the 6 is compared to the 4, and you can see that through the order of the letters. So I'm going to go ahead and make a proportion. I have X over 8, and I have 6 over 4. So it doesn't matter how you set it up, you just have to remain constant in how you are setting it up. So I have colors here to kind of help with that. I have the X and 6 on top, that's from this triangle, and then I have it underneath with the 8 and the 4 on the other side. So you can see I went from green to pink and green to pink both times. You need to make sure you do that, otherwise you're not going to have a proportional relationship. All right, so now to solve this, you guys are going to cross multiply. So we are going to solve 4 times x, which is 4x, and you're going to do 6 times 8, which is 48. The next thing we're going to do is use the division property of equality. We're going to divide 4 on both sides, which gives me a final answer of 12. Super easy, not a difficult problem to do, so hopefully you are able to figure out how to do that. All right, let's go ahead and move on to the next one.
Now, one of the things that I like to do when I have a triangle that is set inside of another triangle and I'm going to be comparing them, I like to separate them. And you're going to see that happen a lot in this course and in future lessons. So the very first thing I do with these 2 triangles is I draw like little mini triangles off to the side showing their parts, so to speak. So I have in my notes a little tiny triangle, and it shows 33 as the height and x as the width, because I know that big triangle is x wide. Then I draw a second triangle, my smaller triangle, and I know 18 is the height, and then I have to kind of look at, ooh, what's the width? Well, it's the total width, x, take away that 25 part because we don't need it. So it's x minus 25. So now I can really see exactly what it is I'm trying to compare here.
And again, the way we know this is x25, we know that segment addition says we're adding 25 to whatever this is, and the total is x. So we kind of want that 25 to go away so that we are left with what x is. So it's always going to be that total minus the part to get the other part. So we are trying to figure out if these triangles are similar. So if they're similar, then corresponding sides should be proportional. So we are going to make a proportion here. The bottoms, we have x and we have x minus 25. And if you did what Mrs. Nett suggested, oh, I can't talk, you should see that the x and the x minus 25 are your 2 bottom horizontal sides. So that's why they went together. And then the 2 vertical sides are 33 and 18, so they went together. And again, you want to stay consistent in how you are setting this up. You want to make sure that whatever you're choosing to put on top in the first ratio, you do the same thing in the second.
You want to set it up like a square, and I tell my students that BS equals BS, big, small, big, small. So in this example, if you'll notice, we talk about the big triangle going all the way across the top. So across the top of our proportions, we got nothing but information on the big triangle. Then if you look at the bottom of our proportion, you'll notice that we talk about nothing but the small triangle.
Exactly.
Now, one small other piece here. You can't just look at the horizontal, the going left and right. We also have to look at top and bottom. So if you look at the first ratio to the left of the equal sign, it is talking about nothing but the bottom of the two triangles. Then if you look at the right, you'll notice on the right side, both of those numbers are talking about the height. So as long as you can make this square where everything is connected, we're talking about the height, we're talking about the width, we're talking about the big, we're talking about the small. Doesn't matter how you or I set it up, we can set it up differently and both be right.
It's also a lot like when you would write your congruency statements. You can name the first triangle however you want, but you have to name the second one with corresponding parts. So however you want to make the first ratio, that's completely up to you, but you have to make sure that the second one you do is the exact same process that you used for the first one. So from here, you're just going to start cross multiplying. You know that, oops, where are we? There we are. 18 times x would give me 18x. And then 33 is going to multiply by both x and negative 25. So we are going to distribute here. So we have 18 times x, and then we're going to do 33 times x and 33 times negative 25, which gives us 18x is equal to 33x minus 825. We can use the subtraction property of equality to get negative 15x is equal to negative 825. And then lastly, we will use the division property of equality, dividing negative 15 on both sides, giving me a final answer of 55.
Easy.
All right, our last one is actually a very easy problem. It looks really complicated though. We're talking about similar triangles, so even though you have a bunch of different shapes here, I'm hoping you guys can see the two triangles that I gave you. We have this little triangle up here, triangle LYI, and we have this triangle here, LTR. So you're also given that BETY is a rectangle. Well, we know a whole lot about rectangles. We know that they have to have 4 right angles.
Opposite sides are congruent.
We have to know that opposite sides are congruent. You know, diagonals are congruent. Diagonals bisect each other. We know a whole lot about rectangles. So this question is asking us to find the perimeter. So we're definitely going to be talking about the opposite sides and all 4 sides actually. You're also given that R is a midpoint of ET. So if the right side of R is X, then we know the left side must also be X. So for this triangle, the bottom horizontal side is X. Going vertically, the height, we can see that T to Y is 4 and Y to L is 1. So this is a total length of 5. So if you want, you could, again, like Mrs. Netz suggested, you could draw that triangle by itself, and you would have a height of 5 and a base of X. The other triangle, you don't have anything about the bottom. You know the vertical height, though, is 1. If I say that these are two similar triangles, and we know that they are actually by angle similarity, let me just explain that really quickly. Well, you know this is a right angle. You know this is a right angle, which means that this is a right angle. And then they share angle L. So by angle similarity, we do know that these are similar triangles. I know this is 1/5 of the green triangle. This height is 1, this height is 5, so 1 is 1/5 of 5. Well, then I also am able to say that the base is 1/5 of x, or x over 5. And again, I know that because we have a 1 to 5 ratio. So I can now start to work this out. Now, that is actually all you need for the similar triangles. We're not going to make a proportion because it's not asking me to find a missing side length of my triangles. It's asking me to find the perimeter of the rectangle. Well, if you remember back to when I first said we had a rectangle, Mrs. Netz pointed out that opposite sides are congruent. Well, I know that ET on the bottom is 2x because it's an x plus an x. I know that BY is 18 plus x over 5, so I am able to write that equation. You guys are now just going to solve this equation for x. I would simplify the left side. 1x plus 1x would give me 2x. And then from here, I believe I did it. Yep, we're going to multiply by 5. I cleared my fraction out. You don't have to do that, but over 5 can get a little complicated, so I'm going to use this little, not trick, but operation to clear that fraction out. So 5 times 2 would be 10x. 5 times 18 gives me 90, and then 5x over 5 would just cancel the 5's out. So from here, you guys should have no issues solving this. We're going to use the subtraction property of equality to get 9x is equal to 90. Then the division property of equality, we're going to divide that 9 out and get 10. So because I know that x is 10, I am able to determine that this side length is 10 plus 10, which would be 20. Which means the top is also 20. We know up and down we have side lengths of 4. So I'm able to now find my perimeter by adding these all together and getting not. So I can add the 4 sides together and I get 48 units for my perimeter. So I was able to, through the use of similar triangles, figure out the opposite sides of my rectangle and then calculate the perimeter. So that is the conclusion of this lesson. Hopefully you guys feel confident that if you have 2 triangles that have congruent angles, we can say the triangles are similar. If you have 2 triangles and the sides are all proportional, you can say the triangles are similar. And then lastly, if you have 2 triangles with 2 pairs of proportional sides and 1 pair of congruent included angles, the triangles must be similar. And then from there, you should be able to create proportions to help solve for missing pieces to the problem. If you have any questions, please reach out to us on Remind or at our email address.
Hey, Mrs. Weichel.
Hey, what, Miss Nuts?
What did the complementary triangle say to the isosceles triangle?
I don't know what.
Nice legs. Get it? Compliment?
I do. I get it. I get it. All right. Thanks for joining us. We will see you in 6.3.